Hello, I'm Radek. I came to CEF in 2015, directly from the embedded business, from the embedded, I was doing before, embedded devices. And in this genre, in this branch of the IT business, a typical practice to deal with a memleak is watchdog. Is a simple device that will restart your application if something goes wrong with, let's say, memory allocation. Over next 20 minutes, I would like to talk about a bug that is perfectly immune to this kind of cure, let's say that way. A memory leak, a reboot could not help with. And this immunity to restart, it's just one of a few superpowers this tiny little bug exposes. Entire list of them. Why this one is so interesting? But interesting in the sense of the old Chinese curse. May I wish you live in interesting times. Nobody reasonable would like to live in such situation. Boring is better. But this one was pretty interesting because, first of all, it's a memory leak, but in a structure that is being synchronized with your disk. Every single time when an OSD boots up, the potentially inflated memory structure is reloaded from a disk. So it's not that if your OSD set enough space, it's not enough to simply restart, to have this OSD restarted by OM killer. It's persistent, but it's a trap. When it happens once, all you can do is to basically redeploy your OSD. And even this, we were afraid that even this could be tricky because of possibility to fetch the corrupted data from another replica. Fortunately, this actually doesn't happen. It was a theoretically analyzed problem. Fortunately, it's not so bad. It's enough to redeploy an OSD. What is also interesting is that this bug was in the code for years, since 2017. It was hidden. It got exaggerated by another change, actually a set of changes. In Octopus, we turned the autoscaler, we changed a configurable defaults value for autoscaler. Before, in Nautilus, autoscaler was disabled by default. This changed in Octopus. It got, for newly created pools, it got turned on by default. Moreover, this OSD bug has roots in another bug, a bug in the libstd C++ library. There is a problem with the size method of the std list container. It's set in the specification into its complexity a time complexity must be constant. In some versions of libstdc++, it wasn't. So when the OSD problematic code got written, it was a different strategy, one that avoids calling the std list size was picked up. And that was the root, the origin, the mental origin of the problem. I will describe in this talk. What is even funnier is that this memory leak has self-healing abilities. If you are lucky enough, which was the typical case, okay, memory runaway happens, but it ends and it gets cleaned before your OSD hits the wall, before it hits the arm killer. To be even worse, it's multifaceted. There are the clinical picture of the illness is very differentiated. It varies among clusters. It depends on the stage the issue is diagnosed on. And unfortunately, it's lethal. The final stadium of the disease is dead OSD. It's a permanently dead OSD. No, as said before, Reboot won't help. You would need to redeploy the daemon. And this could happen as a surprise. If you are running on powerful, memory-rich hardware, it's not so unlikely that you will, the first time you notice the bug will be during the daemon's restart that is related to an upgrade. Plenty of fun in the same sense as the interesting word. Symptoms. Increased latency under I/O traffic. It's emphasized, it's written differently, because this is a new symptom that is actually under research. We haven't thought about the tie of this bug to our latency spikes. They came pretty recently. We are verifying them right now. But what we diagnosed till now, increased memory usage. That's the first thing you could notice when taking a look on your cluster. When the illness progresses, you could also notice, but only if you check your logs, warnings from tcmalloc, large alloc entries in the OSD logs. As the inflation, as the memory run away, is about a structure that is a key for handling the peering and recovery process, you would also expect that recovery takes far longer. It's far more memory and CPU intensive, because you simply need to process a lot of chunks. And when this happens, and your OSD is somewhere close to the threshold of ability to withstand the memory pressure, you can see OSD flipping. And finally, of course, the death due to the uncurable death of OSD because of inability to boot. So, I don't know how about you, but when I first encountered this issue, I felt a bit scary, to be honest. So before going to the weeds, before going to the deep diving to the technical stuff, some heuristics about diagnosing whether you are affected, whether your cluster is affected or not. Heuristics, because, well, in many previous releases, in many releases, there is simply no direct and at the same time unintrusive way to judge, to see the size of the inflated structure. It was actually a thing that nobody was interested before the problem. The structure lacks a lot of tooling, a lot of even debugging facilities. There was no even simple debug with the dupes structure size of the PG lock. But we introduced them. We covered those shortages. But for the sake of being universal, let me talk about those two legacy ways of diagnosis. The conclusive one, which is unfortunately intrusive, requires basically dumping your entire PG lock with the CEF object store tool. What's the problem here? It's intrusive. You need to stop your OSD. Fortunately, there is an indirect way. Dump mempools. It's admin socket command, so you can observe the stats with a very unintrusive way. There is a special item pglock. There is a special entry pglock items, and numbers exceeding millions, or let's say 300,000. It's an orange flag, I would say. Here is a link to a comment where the heuristic is pretty well described. Items are above, let's say, million. Let's diagnose further. Close to the 300K, but on defaults, it's fine. But okay, let me introduce Mr. DAPS issue, Mr. PG lock, DUPS issue. In a short, very dense form, it's simply a problem with a jumped trimmer of the PG lock DUPS memory structure. But what it really is? Let's start with covering what is its parent. What is PG lock? Basically, it's a journal. It's an ordered collection of PG lock entries, and a new entry it's added basically every single time when an OSD handles write-like operation. Then we are generating PG lock entry T, and those entries have multiple purposes. Most people think about, most power users think about PG lock as a mean to facilitate recovery. We have PG lock-based recovery. We have backfill. Backfill is a last resort thing. It requires basically scanning all the objects between OSDs. PG lock allows you to just check the latest operations, basically a journal. But it's not the very sole purpose of PG lock. It handles different cases as well. One example, actually this is a comment taken directly from pglock.h. there is pglog facilitates also support for Erasure coded pools. Actually, it's essential to handle rollbacks, but that's not the interesting case for today. For today, we have the point number 2, detecting duplicate ops. What is that? pglog is being created not only when an OSD peers or handles recovery in general, it's actively consulted even on the hot IO path. If you, when handling a write, OSD looks up in the pglog by the key, which is basically identifier of single request sent by client. There is a request or a requeue ID T structure, ID of a client visible request. And there is a possibility that when IO happens, that an operation has even been completed and replicated over all replicas, but just the ACK sent from the primary to a client, it got dropped somehow. Maybe there is client restart, who knows? Something bad happens to the ACK. Then, when a client handles a non-idempotent operation, like a delete in Rados gateway, let's say, it would regenerate this operation. It would try to re-execute. But if just the ACK is missed, it's reasonable to expect the operation itself got successfully executed. So we don't want to see the client the widths of the network communication. That's the motivation behind checking in the pglog whether operation with this particular ID, whether it's already finished or not. And if it's finished, what's the written code? Whether we should succeed, whether we should say INT, that's taken from the pglog, actually. Those snippets are taken from the Crimson project. It's not the classical OSD. I simply don't know. I think I know Crimson better than the classical one. That's the motivation. OK, we know what pglog is, but let's go finally to the DApps thing of it. And by the way, let's track our progress with the underline. We said that pglog covers multiple use cases. And there is asymmetry in lifetime and data sizes between them, between speeding up the peering process and handling duplicates. Basically, the entries we store in PG dupes, they are shorter in size, they are lower in size, but longer in time life than the PG or log entry Ts used for the sake of recovery. We want to, actually the specific need were optimizing use case of running OSD with shorter pglog and which was exposing, which was also lowering the time window a client can get idempotency on its operations. This problem has been covered by introducing the dupes container to pglog. So basically, dupes is just something like the main list of entries, but smaller ones. just for the case of handling duplicates from clients. And new dupes entries are generated solely from original pglog entry. You can think about that as a compression. We are compressing, lossfully compressing pglog entries into dupes entries. It happens in the trim, during the trimming operation of pglog. There is a threshold if we exceed number of pglog entries. We can convert some of them into smaller dupes entries. Just an optimization. But of course, if we are pushing, if we are adding the converted, that's actually exactly the place when the compression, when the conversion from log entry to dupe entry happens. We are adding them to the list. And here it works basically as a queue. So there is the generator, and of course, there must be a trimmer. It's another part of the same method, of the trim method of the pglog. We are just popping it back. But if there is a trimmer, what would happen if this trimmer got stalled? Here, those two lines. We are verifying the version of dupe entry and comparing against last added pglog entry minus some kind of minus a constant, a configurable constant. This was the fix. This was the workaround for the libstdc issue with the size method of std list. Dupes is actually is typed as std list, and we wanted to avoid calling it. Instead of taking the size directly, we started to work around it by comparing a version. It was, well, it was a bad idea. What makes the self-healing ability is the relationship to the recently added log entry. So in theory, you could fight the issue, the problem, by basically hot adding memory and hoping that finally the corrupted entry, its number will stop being larger equal than the thing derived from the recently added I/O. Of course, the question is how much memory you can add to a node. But it was also a contributor to the disappearing nature of the problem. We are tracking it for a long time. There were community reports about problems that at some time simply self-cured, disappeared. Oh, need more info? Sorry, now it works. Hard to catch. But just the susceptibility of the trimmer doesn't automatically translate to a problem. you need to have some kind of source, some kind of generator of such corrupted dupes entries. And it is, unfortunately. It is the split operation on PG. And that's the link to the autoscaler. So a question from developer to the community. How often do you manually increase the number of PGs in a pool? I would say quite rarely. But autoscaler does it extremely frequently. It calls the same code paths, but in a far more extensive manner. So if there is any suspectability, it's far easier to have it uncovered if you turned on the PG autoscaler. It executes the same code, but more frequently. And the issue is that when we are splitting a PG, of course, we need to divide. The PG log entries that will go to new, will stay to the old PG. But we were simply copying the dupes list between those, from old PG to new one. It's simple. It's not even stupid. It was based on the assumption that the trimmer is taking into consideration the size of the list. But it stopped because at some moment because of the libstdc++ issue. Oops. Yeah. If you dump your PG log, there will be the dupes list as well. And if you are seeing that at the beginning of it, there are entries with version number far higher than the head of the log, yeah, then you are affected by the issue. That's the ultimate confirmation of the disease. That's actually how the structure of jumped trimmer looks like. It's well, I attached this slide, and without the hope it's easily readable. The reason was authenticity, because we made it was a team effort, huge team effort, multiple developers, multiple people, many testers, deployment engineers. Huge number of people were involved. And we made some hand notes. That's one of them. It's original. Okay, so what got changed? That the problem we had for years started appearing pretty recently. The main thing is turning autoscaler, the PG autoscaler, on for freshly created pools in Octopus. Fresh created. Okay, if you are migrating pools from older, if you are upgrading Ceph and you have already pools, the autoscaler is not automatically turned on. It's its setting, autoscaler settings is being preserved. It's about newly created pools. Also, there was a change about some developer level configurables that are controlling the conversion process. It's not obligatory that, and basically that's a hint for another workaround. The conversion of regular big PG log entries into smaller dupes entries It's not mandatory. It's well configurable. You can find even settings that will completely ensure that the conversion never happens. So it's a possible way of prevention. But how about the fixing part? It took a few months since the diagnosis to finally release the patches. The prototype of them got available pretty quickly, but it was buggy as well. And let me explain the strugglings, the problems we encountered when fixing this issue. There are two ways how pglog entries get trimmed. First one resides in OSD. That's the default, the typical way of trimming them. It happens automatically. It happens it's called on the right path. When you are adding new entry to the pglog, you are also trimming older entries. That's the main way. But there are some developer / deployment engineer targeting tools, especially Ceph Object Store tool, that's purpose is to help you with disaster recovery, basically. And all those tools were aware about pglog for years. But this tiny little dupes, it's so small. It goes unnoticed when it comes to those offline tools. COT, Ceph Object Store tool, was perfectly unaware about the dupes. There was no way to trim them. While the online, the in-OSD trimmer was jammed. Even more problems. Diagnostics. I mentioned about lack of debug facility that is the same time direct and unintrusive. There was even no single debug entry about the size of the dupes section of the pglog. And of course, it was never ever printed when it comes to CLI tools, like Ceph pgquery, something like that. It was unaware as well. It wasn't covered on tautology. There was even no way of course, there was no way to breed millions of those dupes entries to verify our fixes work. This had to be developed from the ground up. Because, if your trimmer is jammed, initially you won't notice. To be honest, it will be fine very likely for weeks. Even I would risk saying it will be fine for months, maybe even years, till you accumulate dozens, maybe even hundreds of millions of those tiny little 71 bytes long, if I recall correctly, on dupes entries. It accumulates over time. And deploying a cluster and staging it for a few years, for a few months, it's really not an option. We cannot wait. So we had to develop some kind of injector to breed those entries in orchestrated way, let's say. And moreover, the online trimmer, it was it was pretty hard to engineer robustly. I will cover that soon. Because of those problems, we decided to split the fixing into two phases. First one, less ambitious one, let's say, was mostly about the COT, about the offline tool. We implemented a dedicated command called trim pglog-dubs that is completely independent from the online trimming code in OSD, at least in the final fix. Initially, in the pre-prototype of the patch that was released very, very early, we reused the trimmer code from the OSD itself. And this exposed another problem because in the OSD arrangement, dubs and pglog trimming are highly coupled. Not even between each other, they are coupled even with updating pginfo-t structure that is used during recovery. Calling it from COT just to trim dubs missed this part, and was a reason of basically diverging the pglog from pginfo-t. Fortunately, those patches were never released publicly. Are available, of course, in a bug tracker, but it was a prototype. So we introduced the extra feature to COT. We also added just a debug to OSD code. Not something that is exposed to user, and there was a good justification for that. Bug complexity, avoidance of bringing new complexity for the sake of bug portability of the patch. It was bug ported basically to every interesting release, and it had to be simple as possible, while adding even a extra single column to the results of PG query operation would impose changing of our encoding formats. Actually got noticed that that I have 1 minute and the clock desynchronized. Okay, let me speed up. Offline trimming has been covered as a measure for targeting as many releases as possible. Online trimming, the ultimate fix. We want to trim all those junks, but it's a problematic. Try to imagine upgrading a cluster that hiddenly accumulated tons of those entries. You cannot reliably remove all of them in one simple go. You would very likely hit problems with RocksDB, with Bluestar, with many other places. So we had to be extremely careful here, as any prolonged activity during OSD boot up can easily lead to marking OSD down and breeding extra peering process, which is of course also about exchanging those terribly inflated dubs lists. So, not easy thing. we also imposed on ourselves hard complexity limit. We wanted to have the fix as simple as possible. And actually, if somebody is interested how it looks from the complexity point of view, that's the stack of all places where we must avoid inflation, where we must take care about some extra quirks, like generating tombstones in RocksDB. Unfortunately, I don't have time to cover them today, but you can ask offline me, Mark Nelson, anybody rated, or Adam Kupczyk, anybody in the Bluster business to see how painful could be trimming of how painful could be generating of tombstones in RocksDB. So what we did, a warning. We kept it as simple as possible. We are trimming those inflated entries. Yes, we are doing that, but over a prolonged period of time. We are mixing those deletes with regular writes to pglog to not accumulate too many of tombstones in RocksDB. And if the problem is painful enough to result in OSD slowness, I think that every reasonable operator will check logs, and then we see the entry and the hint to switch to offline trimming. Terrible thing, but interesting. Thank you very much.